Okay, so this is our graphing and looking at seeing the application of exponential decay functions. So you should have out your 7.1 note-taking guide as a reference because you're going to see a lot of relationship between this and that lesson. This should be quite a bit shorter, and I'm going to go a little bit faster. Make sure you understand 7.1 before you go on to 7.2 because this will be more abbreviated. You see that I already have the definitions for exponential decay function and decay factor. You're going to see that an exponential decay function has the same equation, y equals ab to the x power. A is still going to be greater than 0, so positive, but b is going to be between 0 and 1, which means that the base of the exponent is either going to be a fraction or it's going to be a decimal. So that makes it between 0 and 1. It still isn't negative though. Okay, so, and then the decay factor again is b. It's just that now b is this between 0 and 1 amount. So you should pause the video and write that definition in. Okay, so here we see the parent function for exponential decay, and it's still y equals b to the x. It's just that we're looking now where b is a fraction. And the usual fraction that we use for the parent function is 1/2, which is exactly what is graphed here. So we're actually looking at y equals 1/2, that's 1/2, sorry, to the x power. And notice that 1/2 appears in a fraction, or excuse me, in parentheses, because if we didn't put it in parentheses, the exponent would not go with the 1 and the 2, and it needs to. Okay, so we graph it in the similar way. We're going to put 0 in for x. So when we put 0 in for x, we get y equals 1/2 to the 0 power, which of course equals 1. So we have our point 0, 1, which is graphed here. And then we put in 1. Y equals 1/2 to the first power, which gives us 1/2. So we have the point 1, 1/2, which is also graphed here. And then we draw the curve. Notice the difference in shape though. Instead of starting low on the at the asymptote, it's starting up high and coming down. So the values are getting less and less and less, in this case by 1/2 each time. Many things in the real world decay exponentially. As a matter of fact, that's why the word decay is used, because anything that is decaying decays exponentially. Another thing that decays exponentially is nuclear elements. So plutonium, for example, we give it a half-life, and they have very long half-lives, which means it takes a long time for their power or their nuclear, I don't even know how to explain this, but for the particles that are being driven off them to be cut in half, for them to decay to half as much. So because of that, because it takes so long for them to decay, that's why we don't like nuclear waste. It takes a long time for it to go away, and it's bad stuff, right? So many things decay exponentially. The domain of the function is still all real numbers. It's going left forever and right forever. And the range, we still look the same way. We still have this asymptote, which for the parent function is along the x-axis. The difference being, though, that there really is no difference in the range. I mean, it's still a wall, you know, kind of an idea, that asymptote. So we still write it the same way. We'd have in this case y is greater than 0, not equal to, just greater than, because of that asymptote. Or, as I told you before, you could write 0 is less than y, which is less than or equal to infinity. All right, so we are going to graph this. It's going to be graphed the same way as the other ones were. So I'm going to pause this, graph this, and then we can look at it. All right, so I found my plotted points here. I put 0 in for the exponent. And of course, what's different about this function, besides it being exponential decay, is also that our a value is now negative. It's still exponential decay. What makes it decay is not the negative a value. What makes it decay is that our b value is a fraction, less than 1, so 3/4. So that's make sure you understand that's what makes it decay. So in this case, our asymptote is still at the x-axis. We have no h or k shifting it. So I've plotted my 2 points that I found by putting in 0 and 1. And when I draw this, it's going to be easier if I start at my asymptote up here at the x-axis and then draw the curve going down. Okay? This is still decay, but it's something like this. We have something negative, and the negativity is decaying. So for example, let's say we owed some money, so we're in debt. Well, and we're paying off our debt. We're paying 3/4 of it off at a time. So if we owe $100, the first time we would pay off 3/4 of that, which is $75. And then the next time we would pay off 3/4 of $75, which or $25, the remaining balance of the loan, which is, I don't know, like $15. So we pay that off. And then of what's left, we pay off another 3/4 of that. So you see what happens is we're constantly paying off 3/4 of what we owe. So in theory, we would never reach $0 because we're only paying off 3/4 each time. And so that's the way that works. So our plotted points were 0, -2, and 1, -3/2. And we began just below the x-axis, and the reason we began below the x-axis is because it's that negative a value, flipped it over and put it underneath, and it passed through our 2 points and moves down as we go to the left. So that's why I began over here on the right and drew it down, because it's nice to start at the asymptote and then draw from there. All right, we'll go to the next one. Now we have our h and k, so just like before. All right, so I put in my values over here on the left, and I got 0.165, and then I used 0 and got 2. And I just now noticed that the note-taking guide wants us to use 2, so I'm going to do that really quick. Y equals 2 times 3/5 to the second power, which will give me 2 times 9/25. I square the numerator and denominator. 2 over 1 times 9/25 will give me 18/25. Now I have to kind of picture 18/25. You might want to use your calculator and look at that as a decimal. It might be more clear to you. So 18/25 is approximately 0.72. So that gives us a little bit maybe easier thing to think about when we graph. That's at about 0.72. So I'm going to start at my new origin, as we call it. I'm going to plot point from there. 0, 2 is just up 2. 0.165 over 1. Well, 6/5 is a little bit more than up 1, so I'm going to put it about there. And then 2, I'm going to go over 2 and up 0.72. We'll put that about there. I'm going to draw my asymptote, which I remember goes always through our false origin, as we call it. The equation of that asymptote is y equals 1. Notice that still matches our k value. Okay, it always will. So now to graph this, I'm going to start at the asymptote and then follow my plotted points. I want to try to avoid letting this end of the line head upwards, because it's not a parabola. It's not going to go back up. It's just going to keep going down closer and closer and closer to the asymptote. It's never going to turn around and go back up. So it goes through 0.2, and we just use 0.72. The asymptote is at y equals 1. The domain, left and right forever, so all real numbers. The range, again, it's above our asymptote, so y is greater than 1. Or 1 is less than, not equal to, my error, sorry. y, or 1 is less than y, which is less than or equal to infinity. Okay, moving forward. Here are two for you to graph on your own, and I'll graph them, so pause the video, graph those, and then come back. Okay, I've plotted my points. I'm just going to draw my graphs now. I have my asymptotes sketched. We're going to notate that the equation of this asymptote is y equals 0. That's our horizontal axis. This is y equals -3. The domain here is all real numbers, and the range here is y is less than 0. The domain down here is all real numbers, and the range is y is greater than 0. So this, I'm going to start at my horizontal axis and just come up here through my points. And here I'm going to start at my horizontal axis, and I'm going to come down through the points. Okay, that would be our graphs. By all means, you should watch the video more than once if you needed to see that again. The calculations are over on the left. The ones that on the top are the calculations for problem number 1, and these down here underneath are the calculations for problem number 2. So now we're just putting our numbers into the decay model. So the decay model is y equals a, which is our starting amount, times 1 minus r to the x or t power. It's oftentimes t, where a, again, is the starting amount, just like we had before. R is the rate, which is a percentage expressed as a decimal. And t is the length of time. So down here we have this problem, which you might want to pause and read. The beginning amount for the cost of the television is $1,200. And it loses value over time. It loses value by 21%. 21% is 0.21. So once again, you can take 21, divide it by 100, and you're going to get 0.21. So our model is y, the ending amount. That's our ending amount always over here. Our ending amount is our beginning amount times 1 minus our decay rate. That's the big difference from growth. Now we're subtracting because things are going away instead of getting bigger, to the t power. They ask us up here to estimate the value after 2 years. So we're going to put y equals 1200 times 1 minus 0.21, or we could simplify that, and 2 years would be to the second power. We could take that 1 minus 0.21 and we could change it to 0.79, and that would be fine. You can do that. You don't have to, but you can. As long as you keep it in parentheses, you don't have to. So then take your calculators and calculate that. Okay, I calculated it, as you can see here on the calculator, and got a very small amount, $52.92. So it lost a lot of value, which some things do. Some things lose value very quickly. They tell us we can graph it. I'm just going to tell you, graph it on your graphing calculator. You can look for the asymptote. You will not see it graphed on your graphing calculator, the asymptote. But where do we look to find our asymptote? We look at h and k. So since there is no k, our asymptote is still the horizontal axis. It's just that this is going to take a little bit of time to get there. Okay? But you can look at that on your graphing calculator. I'm going to graph it on my graphing calculator and show you what that looks like. I'm going to pause. I've got to make this quick because this is going to end, but I did recalculate that, and I thought that was a mighty big jump down, and it would be $748.92. I apologize for that, as you see on the calculator here. The graph, I put in the equation. You're welcome to pause and look at that. Here's the graph. You can see it going down, the decay. Okay, and that's the way that works. I'm going to stop this video and we'll start